Now let's review a checklist of analysis tasks, and I'll tell you why you might use these different tasks. First of all, we can find the top talkers on a network, and that's important because if the top talkers suddenly change, you may have some compromised hosts on the network. Also, you may want to allocate bandwidth accordingly. You can identify the protocols and the applications in use. Now, this can be used for security purposes, certainly. If you suddenly see TFTP showing up and you don't expect to see that traffic, that should alert you to do a little bit further investigating. You can figure out the average packets per second rate and bytes per second rate of an application or all the network traffic. For the application, this is nice because you can get a general idea of how quickly an application should be able to function across a network. You can get a list of everyone who is communicating, not just the top talkers, but everyone that's communicating. If you start seeing hosts that you don't recognize, you may want to investigate that further. You can also get the packet lengths used by a data transfer application because, of course, transferring data using maximum packet sizes is more efficient than using minimum packet sizes. You'll also be able to detect the common connection problems. So if a source tries to connect to a target and gets a refusal back, we'd be able to detect that very quickly and understand why the application isn't functioning. We can also easily spot delays between client requests due to slow processing. We can spot delays between client requests and server responses. We can spot delays between handshake requests and handshake responses, etc. Here are some additional tasks that we can perform using network analysis. You can easily find misconfigured hosts, as I showed you earlier when we detected a server that did not support selective acknowledgements or window scaling. We can also find network congestion and host congestion. Now, network congestion is typically seen as packet loss, where something along a network is dropping packets. Host congestion can often be seen by a host running out of receive buffer space. We can also identify asymmetric traffic prioritization, where traffic running in one direction across the network has a higher priority than traffic traveling in another direction. We can graph the HTTP traffic to examine any website referral rates. So when you send a packet to a specific website, we can easily find out if that website is telling you to go somewhere else, causing you to basically go to another server to get information. That's also referred to as an HTTP redirection. We can detect unusual scanning traffic on a network. So if someone's using Nmap against you, it's pretty easy to detect that traffic type. We can quickly find HTTP error responses, as I showed you in the last section. And we can also quickly find VoIP error responses, as well as error responses from any application. We can build graphs where we compare traffic behavior to the time when everything was great and you have high spiky mountains in an I/O graph, to when things start looking much worse, when we have low rolling hills and it takes longer for a file transfer. We can also graph application throughput, so we know what the throughput rate is for an application, and we can compare that to the overall link. And that way we can get a general idea of how much bandwidth an application requires. We can detect when an application doesn't use encryption as well, because we can clearly read the communication sent back and forth between the client and the host. We can play back VoIP communications to hear the effects of network problems as well. We can also perform passive operating system and application analysis. We can detect different operating systems on the network and different applications. We can spot unusual protocols or unrecognized port numbers very quickly. And when I mean unrecognized port numbers, I mean these are port numbers that Wireshark does not recognize. We can see in the protocol hierarchy window that Wireshark says it's just data. because it doesn't understand the application in use. I recommend that you take a look at the Analyze Suspect Traffic course. We can also examine the startup process of hosts and applications on the network, so that when someone complains about performance during startup at a later date, we now have a great baseline showing us what this should look like, and we can compare it to the current time to find where the problem may be. We can find the service response times for various applications. The service response time is the time between a request going out for some service and the actual response coming back. We don't care about things such as acknowledgments when we're measuring the service response time. We can also graph intervals of periodic packet generation. So when your host is silent, in other words, you're not using it, it's never truly silent, because in the background you'll always have some traffic going out from your host. A lot of times that's due to things such as your virus detection tool that goes out periodically to look for an update, or you may have other applications running in the background. It's a good idea to find out what applications run without user intervention, and then determine if those are normal or if that's a sign of malicious activity. This is just a short checklist of the things you can do with network analysis. And as you go through these courses, you'll realize how many other things you can do once you start picking up the packets.